Hello students, welcome back. We just completed section 1, which concluded with the fundamental theorem of arithmetic. Here's a finite product expression of the prime factorization, and here is infinite product expression of the same thing. Please remember both. Now let's go to section 2 and let's discuss how to utilize prime factorization to the theory of divisibility. The divisibility and prime factorization are related, of course. Here's one way to express relation. Let A be this prime factorization, and A is going to be the dividend. And B divides A means B has this prime factorization. No other prime factor, so A has P1 through Pk, the dividend. The divisor cannot have any other prime factor. And then the powers must be less than or equals to the powers of A. And of course, everything has to be greater than or equal. They're all 0, then of course they're all 0 and B is 1. And that's a factor, yes. And then all equals to AI, then that means another trivial factor, A itself. And then somewhere in between, we have all those kind of things. Infinite product expression is here. So we have all primes, and then all primes, and then B divides A means the powers BI is less than or equal to powers AI all the way. And then, of course, if AI is 0, then squeeze in between BI will be 0 as well. That's going to be a little bit more convenient for us in terms of proof especially, so let's prove it. So we have both directions here. So we have proof both of them, and the proof of the necessity is going to be a bit easier. That is, assume that BI is less than or equal to AI for all those, and then let's prove B divides A. That's going to be a bit easier. And then after that, we are going to consider the other way around. This direction is pretty much straightforward. Just define B that way. All those are given, so define B that way. And then calculate N over B. Then we just have AI minus BI power. And look at the power. Maybe a little bit bigger font is going to help. Look at the power. AI minus BI power. Those are all greater than or equal to 0. All right? These are all eligible powers because AI is bigger. So what do we have? We get a finite product of primes. So that's an integer. That's a positive integer. So flip B to the other side. Then we get A is B times some positive integer. There you go. B divides A. So that's a little bit straightforward. Now let's consider the other direction, and that's going to be a bit trickier, but still not too bad. Recall that B divides A means A can be written as B times C. And then we're going to apply the prime factorization theorem, or the fundamental theorem of arithmetic to A, B, and C. So B can be written like this, C can be written like this, and A can be written like that. So, all right, that's A. All right, how do I write? Yeah, okay. A, and then B, and then C like that. And then this is B, highlighted in green. This one, highlighted in this magenta. And then A, highlighted in blue. And then compare. This and this time that must be the same, and if you calculate those out, and we're simply adding up the power. Okay, I'm running out of color here, so let's just keep it that way. So AI is BI plus CI, and CI should be coming from the whole numbers, so it should be greater than or equal to 0, so greater than or equal to BI. So using the fundamental theorem and the infinite product expression, we can prove this easily. A little bit less straightforward than the other direction, but still easy. So what if you have a divisibility? That means all the prime factors of the divisor must belong to the dividend, and then the powers must be less than or equal. That's the criteria. Now, how about the GCD and LCM? Even more straightforward. GCD, simply take the minimum powers. LCM, simply take the maximum powers. By the way, we had been doing this from elementary school days. As for the proof, pretty close to one-liner as a matter of fact. I wrote quite a bit more, but the idea is little more than just one-liner as a matter of fact. Di is the minimum, so it's less than or equal to both ai and bi. Therefore, d divides both a and b. Okay, so common divisor. And then, all right. It is a little bit more than one-liner. Sorry about that. Yeah, okay, that's one aspect. Let's see. GCD, we needed 3 criteria, right? Number 1, whole number greater than or equal to 0, and that's trivially true here. We are dealing with positive integers here for entire lesson. And then common divisor, which we just did here. And number 3, we can use Bezout's linear combination expression, or we can use the maximality. Here we are using the maximality. Any positive divisor that divides positive common divisor that divides both a and b divides d. So d must be the maximum, the greatest common divisor. And we can use this because we are dealing with positive numbers only. So c divides a and c divides b both, so this power ci should be less than or equal to both a and bi, so it should be less than or equal to the minimum di, and as a conclusion, c divides d. So common divisor and the maximality, the greatest. How about the proof for the LCM? It's got to be similar. First, common multiple and the minimality. Positive, yeah, that's certainly true because we are dealing with prime number theory here, so all positive only. Even if you have negative, just put a negative sign up front and deal with only positive parts, so we don't have to consider that. Common multiple, because mi is a maximum. Maximum is the greater than or equal to both, so we get that. A divides m and b divides m, so we have the common multiple. Now the minimality. If there is another common divisor, common multiple, say n, so n is divisible by a and also divisible by b, so ni, the power, is greater than or equal to powers ai and bi, both of them. So it's greater than or equal to the maximum, and maximum mi, therefore m divides n. N is divisible by m. So common divisor and maximality. Minimality, this is, we use the maximum here, but overall, m divides n, so it's the smallest common multiple. So common multiple and the minimality put together, we get the least common multiple. Previously, common divisor and maximality, put those together and we get the greatest common divisor. And when we prove the maximality, the minimum showed up. So minimum, maximum, those are kind of intertwining here. A bit confusing when I speak, but when you see what's written, it's pretty clear actually. All right, let's conclude this section with just one more set of properties of GCD and LCM, which we already know actually. Whenever we have a common divisor, the common divisor divides the GCD. And in lesson 2, we proved like this using the linear combination expression. Common divisor divides A and also divides B. So factor it out, we say D is divisible by C. C times some integer is D. That's what we did in lesson 2 using linear combination expression. But you can use the prime factorization idea as well. A, B, and C and D are like these in infinite product expression. And then C divides on B, C divides B. That means Ci is less than or equal to Bi, Ci is less than or equal to Bi, therefore it is less than or equal to minimum. So C divides D. You can approach like this too, using the prime factorization and infinite product expression. Similar property for common multiple. In lesson 2, we used to do something like this. Remember? Division algorithm. And then both are divisible by A and B. And then calculate AB over... that's a bit too much. And then there you have a contradiction unless R equal to 0. So M divides C using the division algorithm. Okay, wasn't too bad. Still, we have to take a lot of steps. But if you use the prime factorization, the expression with this infinite product may get a little bit hairy, but once you get over that initial learning curve, it's much easier from this point on. You see? C is a common multiple, so Ci is greater than or equal to both A and Bi, so it's greater than or equal to the maximum, Mi, therefore M divides C. Pretty clear. Finally, this one. GCD times LCM is A times B, and the proof we did in lesson 2 is pretty hard actually this time. It's even worse than the previous one. These GCD, and then M as product divided by GCD, and we have to prove that this M is the LCM. And then first observation, this is actually A times integer because B divides D, and this is an integer times B because A divides D. So what did you get? We get this M is a common multiple of A and B, and then we can use the previous result. C is any positive common multiple of A and B. Then using this Bezo's linear combination expression, you get the linear combination expression here. So M divides this entire C. This is integer times M. And then we are dealing with positive numbers only. So M is less than or equal to C. So it should be the least common multiple. Tricky proof. But if you use the prime factorization and the fundamental theorem, it's not bad at all. The minimum plus maximum is just AI plus BI, because among those AI plus BI, smaller will be minimum, bigger will be maximum. If you add them up, you're going to retrieve AI plus BI. See the color coding? Whatever is smaller, whatever is larger, if you add them up, we get the same sum back again. Therefore, the proof becomes really easy if you use the prime factorization and the fundamental theorem of arithmetic. That completes section 2.